me 3 times. How did they? He's like, okay, put me down. Oh, come on, play.
My name is, my middle name is Kit, and my sister's middle name is Kat. And my son is super whatever they wanted. They're like, Kat, give me this, Kat, give me that. I'm like, we called your name. I don't have to do anything with that.
Okay. So, sorry I'm a few minutes late. So, many of you probably know that next Tuesday, the 11th, is Veterans Day. It's a holiday. And on the schedule, the lab schedule, I've indicated that what I'd like to do is for the students from the Tuesday, Thursday sections that are not disadvantaged next week, is to try to accommodate them. Some of you in the Tuesday, Thursday section, some of you on the Monday lab, and some of you on the Wednesday lab. So it'll be a little bit tighter in those labs, but I think that there shouldn't be a bottleneck with the instrument. Is that something that people, I think it's important. Is that something people are able to do? The people in the Tuesday, Thursday section, raise your hands. Can you come to either Monday or Wednesday? Is there anybody here who cannot? Okay.
I can come for like the first hour and a half,
Okay.
2 hours. But
Okay. All right, how about you, Austin? Can't, period. Okay, so let's talk about that, all right? I'm going to send this piece of paper around. And I'd like you to commit yourself to either the Monday or the Wednesday, all right? So you don't have everybody or most everybody show up to one of the labs and they won't be able to accommodate.
Wait, so we're only having one lab next week? If you're in the Monday, Wednesday, do you still go to both? Or?
Well, so if you're in the Monday, Wednesday, yeah, you go to both.
Okay.
And then you'll have some extra friends there.
because the Tuesday, Thursday, they still have the Thursday lab. They
Oh,
just want
okay.
Tuesday lab.
Oh,
So
some
if you're,
different-
so if, because Tuesday's a holiday, and there's no Tuesday
I
lab,
actually left.
rather than the Tuesday, Thursday lab,
It's an old one,
miss
too,
out and
so-
only have one lab
Oh, yeah, no,
section.
that's what I have.
I'm opening up the
No, I
Monday
left
or
it.
the Wednesday, so you can go to one or the other for next week only.
Okay.
Does that make sense? So I'm going to send this around. So if you're in the Tuesday, Thursday, sign up. And if you cannot, sign up for whatever you want to do. And if you can't make, put your name here at the bottom and we'll talk, okay? I'll just pass this around to you. So I wasn't able to make it by lab yesterday. Is everybody, things going okay? I went by the lab on Wednesday. It seems like it's going fine. Yesterday, people are progressing. There's no surprises or problems.
Yeah, there's some problems, but it's okay.
Yeah.
We got all
There's enough time.
What?
Yeah, we tried doing the methods of addition, ours didn't work out. So
Okay.
we do it.
Okay, all right. Okay, and you know why it didn't work?
No.
Did you see, I went by the Monday and Wednesday and we wrote out an example of a method of addition on the whiteboard. That was still there probably, right?
Yes.
And did Taylor go over that with people yesterday?
Yeah.
Okay, and the problem that you're having is probably user error, you think?
Probably.
Yeah, okay, it's usually what it is. But the problem that you're talking about
Our
is,
standard curve didn't work out so well.
okay,
So
for lead,
no, for copper.
okay.
Yeah. I don't know why. Like it just wasn't linear. Our R value was like 0.7.
Mhm.
Aren't you guys making like funny directions? or
Yeah, but that wasn't for the standard curve. That was for something else. That was a different mistake altogether. That had nothing to do with our standard curve.
Yeah.
But yeah, we did make fun of it.
Well, usually, like you said, like I've said many times, it's like when you're breaking up with somebody, it's not you, it's me. Usually, it really is you. When there's a problem about things like this, usually it's user error.
Yeah, we're pretty confident.
Yeah, but we're going to.
Okay. Okay.
Who has?
Okay, so make sure that gets passed around. So all the Lab 2 drafts are back to everybody. If there's anybody who hasn't gotten it, I sent the last 2 out this morning to Josh.
Tuesday, Thursday.
What? Me?
Yeah, to you this morning. I sent yours out this
Oh,
morning.
yeah, I saw it.
Yeah, okay. All right, so I sent the last few out this morning, and we summarized some of the common issues that people will be making, and we made these comments on them, but I want to go over them with people. I can meet with people today from 1 to 2 o'clock, is preferred, to go over any comments or questions you may have. And you can come by my office, we'll go meet next door today. If you have questions but you're unable to make it then, stay right after class and let me know so we can arrange an alternative, okay, today. Okay, so first of all, I thought the reports were generally pretty good, right? I know it was a big step up. There's a lot more writing, a lot more information you had to include. There's an enormous amount of data with all the chromatograms and all that was done. And so I think people did a pretty good job of meeting the challenge and putting in complete reports. But there are a number of some things that I think were common in a lot of reports that I want to run by everybody, make sure they're clear that you can address. And I posted this on the website under Lab 2 for the Lab 2 common problems, so you can look at these issues and have them as a reminder when you're revising things. Okay? But I want to kind of go over this so I can explain what these issues were that I just pointed out. And so this isn't in any particular order. So with the Van Meter, many of you did it, but you didn't say anything about it. And I know for the vast majority, if not everybody, you get lines like this, roughly, right? And you were expecting to get lines like this. And so I think it's important to say, to attempt to interpret what you have in the context of what you expected, that you wanted to, because you expected to get some minimum here that you would then use to determine the minimum plate height, that you would then say, this is the optimal separation efficiency of the column, but it's not necessarily the optimal flow rate because it was at such a low flow rate. And we know that we didn't get this inflection here, likely because the current to the suppressor wasn't changed low enough to accommodate that, and we had to figure that out. So the fact we don't get this inflection is really a suppressor issue in how it works with the instrument, and that's okay. But I do want you to maybe mention to say, we expected this, we didn't get it, and some people did mention the suppressor, but some people didn't.
Oh, because if you want us to mention the suppressor when we talk about it.
Yeah, you can say, we know this, we all know it, we talked about it, and it's this, something like this. So that's one thing. Probably half of you put, for the mobile phase velocity, you put just the flow rate. And that's not right, right? Because mobile phase velocity should be in something like millimeters per minute. Okay? And to calculate that, you need to know on the chromatogram what the mobile phase retention time was, right, where it comes out, and you know the column length, and you know the flow rate. Okay? And so this number down here is not the flow rate; it's going to be the mobile phase velocity, linear velocity. Okay? And you can calculate that easily by those three things. Okay? So you'll get this mobile phase retention time from the chromatogram at each flow rate. You'll have that. The length of the column is fixed. Okay, and then you can and you know where it comes out, and you can easily calculate that.
Isn't it just the length of the column over the time for the solving? You don't need the flow rate for that calculation.
You're probably right. I'm just throwing everything in there. You'll get the same relationship, linear. That is, and we'll do the same slope necessarily, but the units. Now, we know that there was bromide. There's an unknown peak in some of the samples, right? And some of you went ahead and identified that by adding bromide. Some of you went ahead and quantified that by generating a bromide standard curve. All that's good. But some of you totally omitted discussing it, so you should make sure that for the unknowns that you have in your sample, some of those you can identify because of the comparison with the retention times with the anions and the standards. That's easy. Some of those you identify by spiking with sulfate. You guys did, right? Or spiking with bromide. You should just mention that, right? Include that in there. Blah, 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 blah. The minute you refer to the spike as a spike recovery, I don't think anybody really did that. A spike recovery is where you actually calculate how much the spike was recovered based on what you expected. So it really is a spiking experiment in order to increase the peak area of what you presume to be bromide or sulfate, whatever you were spiking with, right? And that's how you were identifying, and how you were identifying what that unknown was, because the peak area would go up, it would go up right this way. And it should go up in some proportion relative to how much the spike was, roughly, right? But that's not, that should be said. Okay, blah, 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 blah. Many of you started talking about the specific chromatographic instrument and the conditions of your experiment in the introduction. And what we're looking for in the introduction is more of a general discussion of some of the theory about ion chromatography and how the suppressor works in general, right? Not specific to you in this experiment per se, but just more general, right? And it doesn't have to be a lot, but you don't want to start talking about methods and specific things that you did in your experiment with the ion chromatography in the introduction, right? So you can set those two. Blah, blah, blah. Many of you had a blank that had some real peaks in it, okay? Because they were contaminants like chloride, for example. And if you were to use that blank, and this is the area that corresponds to the chloride peak in your 5A9 standard and in your unknowns, and if you were to use the area in this blank to calculate the detection limit, assuming that this is noise, you'll get a much higher, a inappropriately high or elevated detection limit. Because this is not noise, this is a real analyte peak. It's a contaminant, and whether you need to subtract that contaminant from your samples is a question, but that's not a noise that would be used to determine detection limit. You could use some other place around there to do that, but you wouldn't do it where there's a place where there's an identifiable peak, analyte peak.
For example, for ours, we had similar peaks like this, but it was so small that there was even no point of even subtracting.
That's right. That's right. Right. So you could say, so you could say it's so small. Small is all it's relative, but maybe it's less than 1% or something of my analyte peak. I'm not going to worry about it to subtract that blank from my analyte, but still I know it's not noise. And so the peak area here is much greater than it would be right there for that same interval of time, right? And so it will give you an artificially high detection limit if they use that, right? So you don't need to subtract it necessarily. You can make that judgment. That's fine, but you wouldn't want to use it to determine the detection limit. I think one or two people mentioned about for the unknown, the analyzed triplicate and what the RSD was in terms of an assessment of measurement precision, and most of you did not. So you want to be able to say, how reproducible is this measurement that I'm making in these unknowns in general? And I've made one, for one of the unknowns, I measured it in triplicate, and I have a standard deviation, and I can calculate a relative standard deviation, or a coefficient of variation, from that one sample, for each of the anions in that one sample. And I can maybe apply that, or suggest that reproducibility might apply to my other samples too, right? To give a sense of how reproducible it is. And it was pretty reproducible, right? Maybe one or two people found any literature values for what actual groundwater levels may be for nitrate, sulfate, chloride, so on and so forth, right? And that's always helpful. It's not required, but that's kind of helpful to see how these values compare to what people have actually published. And that would go into discussion. This is something that I couldn't quite understand, but I think one person had a calibration curve that actually included the zero, right? And I think I've mentioned this before, maybe every time, that the calibration curve has to include a zero data point, right? That would be your zero standard. What's your zero standard?
The blank?
The blank. Okay. It's the blank. And so it's got some very small peak area, for that same place in the retention time window that you're quantifying for all your analytes. And it's going to be a very small peak area, but it still needs to be there, right? Because it's plausible that you could say, oh, I got contamination, or maybe my blank is up there, but I'm not even showing the reader where my blank is, and then they wouldn't know that it's a problem. So you want to put your 0 point in for all the calibration curves, recalculate the line, recalculate the equation. Hopefully, and I think based on most people's lines, the equation is not going to change so much that you have to recalculate all your results, right? Because that would be a bummer. But that needs to be for the figures. All right. I want you to, for the chromatogram, whatever it is, to label all the peaks in the chromatogram. Many of you did this, but some of you didn't. And then indicate which ones are actually quantified with that chromatogram.
He wants to label the peaks on all like 20 or 30 or whatever.
Well, okay, now I'm going to get to that, right? So this would be, you know, chloride, and this would be whatever, you know, this would be whatever. And you can label those. The retention times, where you put it here, you know, some people got kind of sophisticated, that's totally fine. But showing a chromatogram where the peaks are not labeled does nothing. And so if I really care, you say, well, if you really care, you can go back to figure 1 where I show my 5-anion standard where I did label them, and you can try to match up the retention times if you really blow this figure up and see that this is actually matches up with the chloride peak up there. Of course, I know it does, but as a reader, that's a lot of work that you're asking the reader to do. And so you should label these peaks, and you can indicate in the caption, which goes at the bottom of the figure, which peaks were quantified from this chromatogram. So now you have 3 unknowns. So you got one chromatogram for the 5-anion standard. You may or may not have one chromatogram for the blank. That's fine, right? And then you have the 3 unknowns, and for those 3 unknowns, you had 3 to 4 dilutions per unknown, right? And so you say, do I need to show, which is what Wendell was asking, do I need to show every single chromatogram for all the unknowns and all the dilutions? And the answer is no. You can show a representative chromatogram for one of the unknowns that captures the peaks that are present in the unknowns for across all the different unknowns, right? And so clearly some of the anions were higher in some unknowns than other unknowns, or not even present in one unknown, but present in other unknowns. Just show a representative chromatogram. That's all you need to do. It says, this is what the peak looked like that I quantified for this dilution. I didn't quantify chloride for this one, obviously, because it's off the scale. And then another one where I got chloride, but you don't see anything there. And this one I quantified chloride. And this would look similar across your three unknowns, right? In terms of, there's a big peak there, you can't see much over there. And so you don't need to show that for all 3, you just show it for one as a representative. And this is labeled chloride. And maybe down here, that little bump is something else, but what you quantified from here was that, and you indicated in the caption. What you quantified here was, you know, whatever this is, whatever that was. So you would have less than all those chromatograms. So, that's your question. And it's subjective to you. If you want to show them all, that's totally fine, right? It's up to you. I don't think you need to across all the dilutions. But the point is, if you do show them, whatever you show, the peaks should be labeled so that the reader can see what those peaks are.
Even if we didn't quantify it in that, you still have to label them?
Yeah,
Okay.
that's the way it works.
Could we label it using the caption?
In the caption?
Yeah,
you
just
go,
the retention time.
can you go left to right? It's blah, 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 blah.
Yeah, I guess.
Yeah, it's less, and it doesn't take, you know, if you're doing this in PowerPoint, it takes like, just put a thing here, you could say, I'll just label it peak 1, 2, 3, 4, 5. Right? And then in the caption, I'll say peak 1 is this, peak 2 is this, or whatever, right? You can do that. I think if you just say left to right, peak blah.
Oh, no, I was saying like using the retention, because I have like a table of the retention times, so say the retention time is so and so.
You can't see those, right?
Oh, yeah, because they're so small.
It's so small, you can't even see what they are. So the goal is, I know what they are, right? This isn't for me, right? This is what you would do if you were writing this up for a reader, is that you would want to help that reader access the information without having to, you know, skip around throughout the report and find it, right? That's the purpose. That's the point of the exercise. Blah, 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 blah. I just said that, right? All right, I already said that. All right, so we're good. Any questions about that kind of stuff? Okay. This is the next report. It's much simpler because it's not nearly so much data to show, and data processing and data labeling and all that stuff. If that's in consummation.
So for the next report, it says that there is no revision for it, but like if we have a draft, can we like run it by you or
Yeah.
the TA, or is that?
If you, for the third report, if you are able to get as far as you can get before it's due, you are more than welcome to seek input from any of us. And we encourage it, right? But, yeah, you bet. Okay, so we're going to talk a little more about atomic absorption, maybe try to finish most of that up today. I want to remind you that I think we have on the schedule for next Friday is the, to do your presentation, is that right? Yeah, you guys got their schedule. Yeah, I have your schedule. Yes. That's correct. So, next Friday, I'm asking you to have an oral presentation, and I'll talk about this more on Wednesday, an oral presentation of your proposed topic experiment for lab number 4. You'll come in, you'll have one slide, you'll put it on a thumb drive, put it on the computer, or you can bring in your own computer, and you'll take just a few minutes, you and your partner will take just a few minutes sort of clarifying or presenting, this is my objective, this is my rationale, this is how I'm going to do it, right, in one slide. And the purpose is that we can all look at that and say, that's a great idea, I see what you're doing, so, you know, maybe I'll do something to complement that. Or to say, there's no way you can do that, how are you going to do that? And you get input so you can go to plan B. I asked people to come in with a plan A and a plan B, right? If you talk to me ahead of time, and ahead of time is like today or Monday or Tuesday the latest, and you get a sense that your plan A is feasible and worth doing and all that, then you don't need to have a plan B. If we don't talk, then and you come in and you're all set, you're going to propose this, that would be like, that's great, there's no instrument here, like somebody who's at Austin wanted to do mercury and fish, right? And, you know, which is technically possible if you get together with one lab on campus who happens to have a cold vapor or atomic absorption instrument that's needed to perform those measurements. Okay? So some of those things I can give input on if we talk first, so they can steer you in something that's feasible. If we don't talk, then come in with the 2 plans, so that if the first one crashes and burns, then you have something else to talk about.
Crashes.
All right.
Wait, sorry. I thought it was this, everyone did their own project. Is partners in
Yep.
projects?
Yep.
Oh, okay, I'm misunderstanding that.
Yes. So all the labs we do will be are in partnership. If you want to go solo, you know, because you don't like anybody in the class. If you want to go solo, that's up to you, right? And it's totally, that's something you want to do. And we've had students do that really wanted to go it alone for whatever reason they didn't have. So, but most of they do it in pairs because the workload is get more done. Okay, so the main point I bring that up is that on top of getting your lab 2 back and conducting lab 3 right now, is you also have to be thinking about what am I going to be doing for lab 4, right? And the planning and preparation, unlike the labs that we've done so far, where everything is in the stock room or the instruments are in the lab, you just have to show up and be sort of intellectually prepared and plan and have it planned out. For lab 4, when you're doing it, you have to do all of it. And so we've had students come at the last minute and say, I've got my list of chemicals I need, and we're like, that's great, but we don't have those, and we can't buy them, and so they're kind of stuck. And so it's really important to start thinking ahead so that if there is planning, any instrumentation or reagents that are needed that may not be readily available in the stock room, that we can assess whether that's possible or not, and if it's possible, try to make it happen. And that can't happen if it all happens in the last minute. All right, so any questions about that? Okay. So I'm going to talk a little bit about atomic absorption today and see if I can finish that off and maybe give an example of a lab 4 example at the end that is an interesting topic that's totally doable. So I'll try to rush through this, not too fast, but rush through enough so we can get to that at the end. Okay, so So when we think of atomic absorption measurements, right, every analytical technique that we might be interested in possesses strengths and limitations. And some of the limitations are the extent to which that technique may be affected or susceptible to different kinds of interferences or problems. Right? And of course, when we talk about an interference, what that's manifesting as is you making a measurement and knowingly or unknowingly getting the wrong answer because of the presence of some kind of interference. And they come in a number of different flavors, and I'm going to talk about some of these in more detail. Right? So like if we think about flame atomic absorption spectrometry that you're doing now, some of these are quite common. So chemical interferences, because you may have the formation of your analyte in the flame environment, amazingly, may form some molecular species and affect the extent to which it can actually absorb into the photons, right? And so you would be under measuring the true concentration because of the formation of those interference. And typically interferences, depending on the method, but oftentimes interferences would cause you to be measuring a lower value that is truly there, right? Sometimes a higher value, but commonly a lower value. So things can chemically interfere by forming compounds with your analyte, which is a problem. Ionization, we already talked that for atomic absorption, we are dependent upon our metal being in the ground state, unexcited, unionized form, right? And if the metal gets ionized, then of course, it's not going to absorb photons to the same extent, depending on what wavelength you're looking at. And the way that's typically dealt with is by adding chemicals into the solution mixture that may suppress that ionization. And I'll talk about examples of that. Right? There could be spectral interferences, which are a real problem, and I'll talk in detail about that. There could be background interferences that usually are due to other things in your sample that could be considered matrix issues that are contributing to absorbance, but it's not atomic absorbance, and I'll talk about that in detail. Right? And the excitation issue is similar to the ionization, except it's not fully ionized. It just gets excited, and if it's excited with electrons in an excited state, then it's not going to absorb the photons to the same extent as if it were a ground state. So one way that we manage some of these interferences is by using a different kind of instrument. And this is an example of a graphite furnace atomic absorption spectrometer. And I'll talk in detail because these are actually much more commonly used than flame atomic absorption spectrometers because they're much more effective, they're much more sensitive, and they're much more effective at making atomic measurements of atomic absorption and correcting or avoiding interferences from different things in the sample. And we used to have one of these available to students in the class, but it's got kind of old and broken, so at this point it's not functioning. Maybe that'll change, but at this point it's not. And I'm going to talk about how this works. The main key that makes this a benefit of an instrument is it has a small tube here. Pass this around. It has a small graphite tube. Don't drop this. And the sample gets injected in this tube, and that tube rests inside of this furnace, and this furnace is wrapped in a magnet. And so rather than use a flame to provide thermal energy to vaporize and volatilize your metal to the gaseous phase, it uses an electrically heated furnace, a small little furnace. So it applies a high current, and for resistance heating, it heats up that tube and passing around to 3,000 degrees or whatever. And that tube sits inside these two magnets, and the instrument turns them on and off these magnets to create a magnetic field around that tube that's cycled at 60 hertz, so on and off 60 times a second. Because under the magnetic field, the light that's coming through from your lamp is polarized, after it goes through polarizer, is polarized differently. It is able to use that magnetic field to perform some background measurements to correct for background absorbance. I'll talk in detail about that. So the graphite furnace, like I said, so your flame AA is 15 to, well, actually, yours is probably 30,000 bucks. These are 80,000 bucks, just like always, you know, that you pay more money to get instruments that have higher capabilities, detection limits, and avoidance of interference and so forth. Right? And a graphite furnace atomic absorption instrument is one example of that. So you know that for your instrument, you have a light source, and you have the component that's responsible for vaporizing or volatilizing your analyte in the gas phase, and the light beam is passing through that flame, and then it goes with the monochrometer, and you measure the relative absorbance, right? And one of the major limitations of this approach is that you have sample coming up here with your, this way, I guess, with the gas, and it has a very short residence time in this flame because it passes out very quickly. And so the amount of time that the sample is interacting with the light, where absorbance can occur, is relatively short. And the way you kind of try to get around that problem is that you constantly aspirate sample, hopefully in a very even way, and that sample is being aspirated continuously, and you're measuring continuously over some, like the time that you set up in the instrument, right? So, but inherently, it's got the problem of the sample has a low residence time in the flame, right? This flame is very heterogeneous in terms of its properties, thermal properties. And elements are very sensitive to the extent they get vaporized and volatilized, atomized, depending on the thermal environment they're in. Right? So you have a relatively heterogeneous environment and things moving through pretty quickly. And so that's a downside. And so to get around that, graphite furnace instruments use that graphite tube that I'm passing around. And they are able to use a much smaller volume of sample, typically around 20 microliters instead of a milliliter if you're using it. And they are actually able to achieve detection limits that are probably about 2 or 3 orders of magnitude better. And so you might wonder, how can that possibly be? That I can use a sample volume that's a 50th of what I'm using on the flame, and I can achieve a detection limit that's 100 to 1,000 times better. Doesn't make sense. But it does. Right? And the way it does that is by using that graphite tube to actually deposit and process the sample and retain it for a long time while the measurement is occurring. Right? I'll tell you exactly how that works. So you've got this thing that they engineered these and they perfected it over the last several decades. You've got this tube that's machined out of pure pyrolytic carbon. Okay? So it's very inert, very resistant, it's very non-porous. And this thing has 4 sides to it, like you saw. 2 sides of it, like this, get clamped into the furnace electrodes, so that when they try to pass a current through it, it doesn't conduct very well, just like resistance heaters, and it gets really hot because of that, right? So the electrodes here get clamped in, and a current is passed through, and through resistance, it's heated up. And then transversely to that is that small little tube that's hollow in the middle. And that tube is aligned up in the furnace so that the light path from your polycathode lamp or whatever light source you're using passes right through that tube. And if you look inside that tube carefully, what you see is that one is it's got a little port at the top. It's about a millimeter, half a millimeter open. And that's where the sample is injected with a little robotic arm. And inside the tube, it's got this little half-tube sleeve that is attached to the side of the inside of the tube if you're looking down now transversely. And it rests up off the bottom of the tube, so there's a little bit of air under this little platform and air all around it. And so your sample is injected into it right in, like, and it's aligned up so it injects 20 microliters of a drop right on top of that little platform. Okay? And then there it sits, and then you program the instrument to slowly heat the tube up in different stages to process that sample. I'll show you what's done. So this graphite tube has been, how it's been machined and engineered over the years is a tremendous advancement in using graphite for atomic absorption. So what you do once you inject your sample in there is you would program the instrument to undergo a series of steps. And so you start by knowing that I've got a 20 microliter or whatever volume drop sitting at the bottom of that little platform. And the first thing you need to do is evaporate it, just like we do in the flame, right? Of the steps where we have to essentially desolvate, evaporate, desolvate, and then vaporize, and then volatilize. It's the same steps that have to sample undergoes in this little furnace, but now you're doing it to a small little drop. Right? And the way you do that is you would have stages, and maybe over the period of 3 minutes or so, is that you would have one stage where you would heat that tube up to 150 degrees C, maybe, where it's hot enough to evaporate the liquid, but not so hot that things are going to boil. And then that's a dry, then you get all the liquid to evaporate off. And the whole time it's happening, you're running some inert gas through the middle of that tube that just flushes all the vapor away. And then you'd raise the temperature to a different temperature, a higher temperature, and that would start to break down all the organic matter in there. And so in the flame, the whole process of evaporation, desolvation, vaporization, volatilization, all that's happening all at once when your sample gets put into the flame, right? It's not very optimal. Here, we separate all the steps, and we can first dry it, then we can cook it, and if there's any matrix in there, like if it's a biological sample or if it's a natural water sample that came from a river where there's a lot of dissolved organic matter, we can heat up in that ashing step to break down and volatilize all those organics. Okay. That can be done anywhere from 4 to 5 to 600, 800 degrees. And then finally, we heat it up really fast to the temperature where the metal in it that we want is going to atomize. Right? And it's going to instantly be getting free it from all the other molecules in there in the sample and get vaporized up into the gas states where it can then interact with the light that's passing through it. And so we see those 3 steps. And if you look at, like, if you were to be measuring absorbance on the light over the course of those steps, you'd see, well, I'm drying it and I get some absorbance. I'm drying it and I get some absorbance just because the water vapor is interfering with the light. So that's not atomic absorption, that's non-atomic absorption. Right? So it's just like steam is blocking the light or it's measuring absorbance. Then I've started to break down all the stuff, any organic matter that may be in my sample, and that produces smoke, like in a fire. And that interferes with the light, but I measure it as absorbance, but it's not atomic, so I'm not making any readings here. And then finally, I heat it up really hot, and I volatilize my metal in the gas phase, and then I measure the true atomic absorbance. And that's, I get more absorbance there, but that's where I actually take a reading. And so if I were to look at measurement of samples, this would be like standards, and this would be relative absorbance here, then I can see that I get a linear increase in the peak height and peak area with increasing concentrations of the standard. And then separately, when I have a sample and I'm measuring absorbance, I get absorbance also that's non-atomic due to different things. I can only make the measurement during the stage where I can actually atomize the sample. So then I can separate that measurement scheme from all these other processes which would be interfering with my absorption. And I'd be measuring this as absorbance because it's a bulk measurement detector, right? But it's not atomic absorbance. It's interfering with non-atomic absorbance. I'll tell you about what that looks like. So if we look at some of these interferences in a little bit more detail, and I'll go through this kind of quickly. So in atomic absorption, if we have interferences, they can be essentially directly interfering because we have an overlap of atomic spectral lines with the analyte that we're interested in. That's relatively rare. More commonly is that there's some indirect interferences. Indirect would be things that aren't accounted for by true atomic absorbance. And when I talk about atomic absorbance, what am I talking about? Just so we're all clear. What am I talking? So if we have atomic absorbance and non-atomic absorbance, what's the difference between those two?
Non-atomic absorbance is molecular absorbance because anything that's not just atoms.
Okay, anything that's not just atoms, right? And so an atomic absorbance is absorbance of the incident photons due to the absorbance of those photons by atomic species. Okay? And how do we hope to ensure that we're only measuring atomic absorbance and that the atomic absorbance that we're measuring is only of the analyte that we are interested in?
We need conditions so that all the atoms or all the particles are in 3 atom states, and then we select a spectral wavelength.
Right. So one is we have a sharp atomic line, and we you say atomic line, that means that we are selecting a very specific wavelength within about 0.05 nanometers of bandwidth, of wavelength width, that we are measuring absorbance at. So one of the ways that we ensure that we're only measuring atomic absorbance and not non-atomic absorbance is to generate very fine spectra of wavelengths that coincide with the analyte that we're interested in, and that we use the monochromator, of course, to select out and measure only at a very distinct wavelength, right? With a very narrow band around, and around that, a very narrow band around that. That's one. So that helps us make sure that we're measuring atomic absorbance. But what if, and I'll talk in detail about this, if we look at the typical absorption profile, say, is that we may have, let's say if I do lambda here, is that what we're hoping for is we have this nice atomic line that we're measuring at a very distinct wavelength that we're measuring atomic absorbance. And if we look at actually the other sources of interference or light that may be potentially hitting the detector if we didn't correct for it, we see that there's also big sources of background absorbance. So this would be atomic, and this would be non-atomic. And so one example of that would be the smoke. It's coming up from the volatilizing organic matter in a sample. Would be generating broadband absorbance that's not atomic. It could be molecular, it could just be physical interference with the light. Okay? And so the problem is, though, that if we're measuring and monitoring this wavelength, because we can filter all this out with a monochromator, and we're only measuring absorbance at this wavelength, that I'm getting absorbance due to all this. Let's say if my bandwidth is here for the wavelength region that I'm able to measure and monitor, I'm getting all this absorbance from background, and this part of it, only that part of it, and coming up here, is from atomic. So I have to have a means to be able to distinguish and separate those two. And so when I think of interferences, rarely do I get overlapping atomic spectral lines. More commonly, I get indirect interferences due to things that are non-atomic absorbers. So I'm going to move past this part quickly so I can get more to that. And I'm going to talk a little bit about how we overcome this. So we're making a big deal in this lab of having you perform method of additions, right? And the reason that we're performing a method of additions and making the copper and lead measurements by flame AA is that we are unsure about what the overall composition is of the samples that you're measuring. We know there's copper in there, we know there's probably lead in there, but we don't know what else is in there. Right? And that's typically the case. And we don't know what else is in there and what impact those other things that are in there may have on indirectly interfering with the measurement of our analyte by atomic absorbers. And so one strategy that we can invoke to address that unknown is to perform a method of additions. And what is the main goal that you're achieving by performing a method of, besides hopefully getting an accurate answer for the analyte concentration? What's the goal that you're achieving by performing a method of addition with your sample?
Trying to see what the matrix sample is.
You're trying to see that, but analytically what you're doing is you are ensuring that you're matching the matrix in your standards with your sample because you're mixing them together, right? And remember I said